Hey everybody, welcome to chapter 5, Introduction to Solutions and Aqueous Reactions. In this chapter we're going to talk about solutions, and then we're going to talk about reactions that use solutions or solutions in reactions and the different types of reactions, and we're going to talk about a little bit on the different calculations we can do with solutions and why they're important. I mean, we use solutions every day in the chemistry lab. And so this will begin chapter 5. If you have a fourth edition, just to remind you guys, if you have a fourth edition, then this is really just chapter 4B. We're still in chapter 4, but remember in the fifth edition, Tro separated chapters 4 and chapter 4 into chapter 4 and 5 in the fifth edition. And so let's go and get started talking about solutions. What are solutions? Solutions are homogeneous mixtures of two substances, and there's two components of a solution. There's the solute, right? That's the thing that's being dissolved. So in the picture there, that's the salt, if you will, and then there's the solvent, and then the solvent is whatever's doing the dissolving. The universal solvent is water, right? So water does dissolve most everything. Obviously, there are some things that it does not dissolve. If the solvent is water, it is known as then an aqueous solution. Now, when we talk about reactions and the different types of reactions, we're going to use states of matter, which are those little L, S, A, Q, G. That's in parentheses at the bottom of a compound of a molecular formula. And so those are known as states of matter. If you see the AQ, you know that is a solute dissolved in water. And so there has to be two components, right? So a solution is a liquid. Solutions can either be dilute or concentrated, right? That's the way we can describe these solutions. Concentrations are dependent on the amount of solute in the solution. So what we can have is a more concentrated solution with a higher number or a higher amount of the solute, or we can have a dilute solution which has a lower amount of solute in the solution. And so concentrated versus dilute. The way we describe these, the way we can tell if a solution is concentrated or dilute is through a unit called molarity. Molarity is a capital M. It is a common way to express a solution concentration. It is the amount of solute in moles divided by the volume of solution in liters. And so it's moles per liter. Now we have to be aware of this M that we use for molarity, because molarity is a capital M, right? It is a capital M. A lowercase m obviously is meters, and it just doesn't make sense in this context. And so we need to make sure we have that capital M. So we talk about molarity, right? Molarity is moles per liter. So what we're going to start doing is we're going to look at how to calculate molarity from a variety of different, or a couple different ways that we can use molarity to help us calculate something. And we talk about moles and liters. If you remember our discussion on density, which is mass divided by volume, that density is a derived unit where we take two different units and you combine them together to make one unit. That is known as a derived unit. And what we're going to see is that molarity helps bridge the gap between the amount in moles and the volume of the solution. And so let's go ahead and look at a couple different calculations that we can do with molarity. So in the first example that we're going to do, we're going to look at potassium bromide. Potassium bromide. And what we're going to have, so remember, set my board up maybe a little bit. Right? So if we remember, molarity is moles per liter. And so what we want to do, and I'm just going to keep this up here just so that we can kind of see it. I apologize for this glare here. I'll try to work around it, or maybe set the board up a little bit more. But the molarity is equal to moles per liter, right? And the amount divided by the volume. Now it has to be in moles, and and it has to be in liters. And so what I'm going to do is we'll just go and rewrite it here. And so what we're going to do is we're going to look at this. And I want to know what the molarity is when we dissolve 25.5 grams of potassium bromide in 1.75 liters of water. So let's say we take potassium bromide, 25.5 grams, and we dissolve it in 1.75 liters of water. I want to know what the molarity is. Well, I can solve that because I have liters down here. Oh, that's right. And if you're yelling at the screen again, that Dr. Bishop, we have to convert those grams into moles. You are exactly right. Again, here comes another pattern. Grams to moles, grams to moles. And so we have 25.5 grams of potassium bromide. And the molecular weight is 119 for every 1 mole. When we do that, we get 0.21429 moles potassium bromide. So 0.21429 moles of potassium bromide. So now we have moles. Now again, remember, significant figures occur at the end of the calculation. And so it's okay that we keep all these. It'll allow us to be a little bit more precise when we round at the end. And so now we have 0.21429 moles. We know, because it was given to us, that we dissolved it in 1.75 liters of water. And so when we calculate that, we know the molarity is 0.122 molar. And then that's our final answer. And again, we have 3 here and 3 here. And so our answer should be 3 significant figures. And so this is just a straightforward, okay, you're given the grams, you're given the liters. How do you solve the molarity? Now, let's look at a slightly different problem. So I'm going to go ahead and erase this. So let's say I want to know how many grams it would take. I want to know how, you can't even see that. Straight down here. Yeah, sure. Grams it would take to make a 0.350 liter sample of 0.5 molar Na2SO4, sodium sulfate. So we want to make now we're trying to make a solution. And so I want to make a half a molar solution. I want to make 0.350 liters of it. And I want to know how many grams of this compound I will need to do that with. Okay, well, we know molarity is equal to moles per liter. So if we multiply both sides by liters, right, liters over here will cancel. We get liters times molarity equal moles. Now, we need to keep that in mind, right? So that if you're ever given a volume and asked to find grams or asked to find moles, or we're going to use this in stoichiometric equations again, where we need to look at molar ratio, we should always be aware, okay, liters times moles or volume times molarity equals moles. And so let's go ahead. So we're given the molarity, we're given the volume in liters, so we can do 0.350 times 0.5 is going to give us 0.175 moles Na2SO4. Okay, but and so we're done, right, with moles. Well, let's think about what we have to do, and what we have to do is we have to convert moles then, because I asked for grams, into grams. And so remember, moles to grams, moles, is a multiply by the molecular weight. And when we do that, we get 24.9 grams Na2SO4. Right, so again, it's a very common pattern that we're doing. Grams per moles, moles per grams, and we're gonna let them go, and we're gonna, or we're just gonna do the calculations. And again, it's just the pattern that we have seen and we have done before. But there's some other things that we can do with solutions that is different than what we have seen before. And so let's go ahead and look at one of those things that we can do. So here's one of those things that we can do with solutions that we haven't talked about, a different calculation, right? So let's say we have a more concentrated solution. And this is actually how we make solutions in the lab, is we have a stock solution, right? That is very concentrated. And what we can do is we can then dilute it down so that from that stock solution, we can make a lot of a non-dilute solutions for the lab, for the purposes of a lab. And the easiest way to solve these problems is using this equation. M1V1 equals M2V2. And what we say is the molarity of the first case, if you will, times the volume of the first case or of the first treatment equals the molarity of, so let's say we'll do 1 as the concentrated. So the molarity of the concentrated solution times the volume of the concentrated solution is equal to the molarity of the dilute solution times the volume of that dilute solution. Now, what in the world do I mean by that? I'm glad you guys asked. Let's go ahead and look at that. Resume share, stop share. So let's go back to the board. And let's say we go into the lab. So you go into the lab and we forgot to make a solution for you guys. And so then we ask you to make one for you, right? So we say, hey, you know what? We actually didn't make the solution. In this case, it's sulfuric acid, H2SO4. And so we have 3 molar. So our stock solution, our concentrated solution is 3 molar H2SO4. And I want to know, and you are asked to make 450 mils of 0.10 molar H2SO4, right? So we're going to take a concentrated solution and we're going to make it more dilute. All right, so how do we do that? M1 V1 equals M2 V2. It doesn't matter which one is 1 or 2. Usually I'm just more consistent just because I want to make sure that I remember what I'm doing. But if you want to, do a different way, you can. If you want to keep 1 concentrated, 2 dilute, that's fine. If you want to do 2 concentrated, 1 dilute, that's fine. You get the same answer. The other thing is, so for molarity, normally the volume has to be in liters. In this case, it really just depends on what you want to solve for, right? If they say how many liters of this, of 3.0 molar H2SO4 is it needed to make this, then your final answer needs to be in liters. But if it doesn't give you a volume, or if it tells you how many mils or just what volume, then you can keep it in whatever's given. So here we're given milliliters, so we can keep it into milliliters. So we know M1, so in this case, I'm going to put the concentrated one first. So we know the molarity of the concentrated one. We're trying to find that, right? So we'll call that X, if you will. We know the molarity of this, and we know the volume is 450 milliliters. This is molarity. So what we can do is we now have 3 times X is equal to 0.1 times 450 is going to be 45. And then what we do is we just solve for X. And so X equals 15 milliliters. If you wanted to, you could turn the mils into liters and solve this for liters. And so we just have to keep track of our units and keep track of what we're using and what we're solving for, because in the end, our answer will be in whatever units we use up here. So we can use concentrations to check, to make different solutions for the lab, to dilute solutions. We can, I mean, we don't usually make concentrated solution this way. We usually make concentrated solution the way that we calculated molarity, right? Well, how much would I need to dissolve to make this? And so, so that's one thing that we can do. We're going to go ahead and end this part here because these are just basic solution calculations, concentration calculations. What we're going to start then to look at is to use stoichiometric principles, right? We talked about that with limiting reagents, theoretical yields, and percent yield in chapter 4. Well, it's going to come back just a slightly different variation here with aqueous solutions and aqueous reactions. And so, but we're going to cover that next time. We'll get into a little bit more about how solutes work, the different types of solutes, and then we'll start talking about the different types of reactions that we can actually study.